everyone and welcome. It is my pleasure to teach you all today via video. So in Analysis Honors Today's we are starting a new unit. It's Unit 4 on vectors and parametrics. And today in 4.1 we are going to get started with Introduction to Parametric Equations, and we will see an application of that, which will be a projectile motion. So here is a warm-up. I encourage you to try a question first before you watch the solution, so you can pause the video at any time to do that. For our warm-up, we have Usain, who is going for a run. He is bored running simple laps, so he decides to run according to the following pattern. He is going to run 512 meters east, then half of that north, then half of that west, then half of that south, and then east, north, west, and south again, continuing to turn left after each segment. We are asked to draw a segment of Usain's strange path, draw a diagram that would represent all the segments, and then if Usain continues running in this pattern forever, how far in total would we actually run? Start this, pause the video, and then look at the solution later. So, if we were drawing the diagram, what we would notice is that he starts running east, then he goes north, then he goes west, then he goes south. So it's going to be like a spiral that consists of straight line segments. And now to figure out how far away from his starting location he will end up, I would recommend looking individually at the x direction and at the y direction. So in the x direction, so east-west, he goes 512 east, but then he goes 128 west, then he goes 32 east. So what this makes a geometric series with quotient of -1/4. So the sum of such geometric series is the first term divided by 1 minus the quotient. That way we get 409.6 meters in the x direction. Similarly, in the y direction, he goes 256 meters north, then 64 meters south, then 16 meters north, and so on. So if I add this geometric series, I get 204.8 meters. And now using the distance formula in 2 dimensions, I'm going to square each, add them together and square root, getting around 457.95 meters. That was the warm-up. And now we are going to start thinking about parametrics. So, parametric equations, it's a model with 2 variables, where each is a function of a third variable that we call a parameter. This third variable that we use to model is typically the time. And so parametric equations, if we consider x and y, come in pairs and are considering a certain range or domain for the variable t. So here is an example. X as a function of t is t squared minus 2. Y as a function of t is 3t, where t is from the closed interval -3, 2. We are asked to make a table of values, columns for t, x, and y, and graph the equation in the xy plane. I encourage you to try this question yourself first. And this is how it would turn out. So going with t in the closed interval from -3 to 2, I just did integer values here. I can find values of x and y that correspond by plugging into the equations. So to find x, I would square the value of t, that would be 9, minus 2 is 7. To find the value of y, I would multiply t by 3, so that's -9 over here. And then in the xy plane, I can plot one point at a time. So I can plot the point 7, -9, 2, -6, -1, -3, -2, 0, -1, 3, 2, 6. And I can also notice that if our value of t was in the closed interval -3, 2, that tells me that we can also find what corresponding intervals would there be for x and y? So looking at the graph, x goes from the vertex, which is at -2, to this is the farmost point, that's the x value of 7, while y goes from -9 to up here 6. All right. So this parametric equation can also be changed into a rectangular form, meaning we can express y as a function of x. We call this process eliminating the parameter. And if we were to do that in the example we just worked with, what we could do is simply express t as a from the equation y equals to 3t, so t is y over 3, and then I take this expression, plug it back into the equation for x, so I would get x is y over 3 as a quantity squared minus 2, so that is 1 over 9 y squared minus 2. To make sure that this rectangular form of an equation represents exactly the same graph as this parametric equation, we would have to also include the intervals for x and y. X goes from -2 to 7, y goes from -9 to 6, which I previously explained in the graph. So here are some examples on eliminating the parameter from the parametric equations. So the goal for 1a, b, and c is for you to write the equation in terms of just x and y without t. And then in part 2, start thinking about how the domains and ranges work. So how would this rectangular curve relate to these options for parametric equations? Try the questions yourself first and then watch the solutions. So in 1a, we had x equal to root of t plus 1, y equal to t minus 1. So it is easier to express t from the equation for y, so that's what I'm going to do. T equals y plus 1, which also means if I plug that back into the equation for x, x equals square root of t plus 1, that means x equals square root of y plus 1 plus 1, that's y plus 2. I can square it and represent y as x squared minus 2. This is the rectangular equation, y as a function of x. In 1b, we had both of them linear equations, so it doesn't really matter. It's equally hard to express t from either one of them, equally easy in fact. So for example, if I write t from the equation for y as 2 times quantity y minus 1, then I can plug in t into the equation for x, simplify, express y on one side, everything else on the other, as y equals x plus 7 over 4. That's the rectangular equation where I eliminated the parameter. And then in 1c, that one's slightly more interesting because both the equations for x and y involve a trigonometric function. So instead of trying to express t, I will take advantage of some trigonometric identities. So if x is 2 cosine t and y is sine t, I can easily find expressions for cosine squared t and sine squared t. And we know that sine squared t plus cosine squared t makes 1, so that way I can see how the rectangular form would just be x squared over 4 plus y squared equals 1. Question 2 gave us a rectangular curve, y equals to x minus 1 squared, so that's some sort of a parabola. And they wanted us to analyze whether the parametric equations in parts A, B, and C represents the same curve. So what I noticed there is that if I just plug in the expressions into the equation, like put t for x, I will get t minus 1 squared, so A seems to be matching. Same in B, if I just plug in t plus 1 for x, I get t plus 1 minus 1 is t, square it, that's t squared. That seems to be matching. And I believe the same thing will occur if I do part C. So plug in root of t for x, so that's root of t minus 1, square that, that's t minus 2 root t plus 1. So all that seems to be working. The problem is that in this equation right now, even though the equations represent the same curve, the graphs do not exactly match because the domains are different. What I mean when I say that is that in this equation, I can have x positive, I can have x negative, that's all fine. But in this equation, x will only come out as a positive value. So I would have to restrict the domain to make those equations actually match. Which brings us back to thinking about 1a, b, and c, because there might be some restrictions we need to think about. So if this equation was to exactly match the parametric equation in 1a, I would have to add that x is greater than or equal to 0 and y is greater than or equal to 2. In b, x and y can be any real values. Everything is nice and linear, no concerns there. And then finally in 1c, I would have to restrict x to be between negative 2 and 2 and y to be between negative 1 and 1, all inclusively. That is to describe all of x equals to cosine t and y equals to sine t. Think about the range of those trigonometric functions that leads to these intervals over here. All right, parametric equations can also be used on a calculator. So here are some instructions on how to do that on TI-84 or TI Inspire. I encourage you to test this out and play around with the calculator a little bit. We can also use Desmos to visualize parametric equations. There, I encourage you to pay close attention to change in the interval for t, so you see the entire curve, not just certain parts of it. I added some links over here for this problem where you are asked to graph it on a calculator or Desmos. So if you have a calculator on hand, try to graph those. The equations should come out as the following graphs. It's half of a parabola, circle, a ray, and this funny donut. If you would like to watch a video on how to do parametric equations on TI Inspire, the video is also linked in the slides over here. You have access to the slides in my public folder. Here are some thinker questions that you are welcome to discuss with an elbow partner if you have one at the moment. So without a calculator or Desmos and without eliminating the parameter, graph each parametric equation where t is any real value. We have 3 parts to it. And then graph the following parametric equations. They have 2 asymptotes, so your job is to find what the asymptotes are without eliminating the parameter and without using Desmos or a calculator. So if we look at question number 1, if I was to graph in the xy plane the parametric equations x is t and y is t, that simply makes x and y equal. So I would have the entire line x equals y. If I was to graph x is t squared, y is t squared, that also makes x and y equal. But because of the square, I'm only getting a ray starting at 0, 0, and then following along the line y equals x. Finally, in part C, x is sine t, y is sine t. That also makes x and y equal, but if you think about the intervals, sine t has range from negative 1 to 1, which is why we are only getting a line segment from negative 1 to 1, 1. And then if we look at problem 2, the hint there was that vertical asymptote is at the x value that makes y go to infinity. And the other way around, horizontal asymptote is the y value where x goes to infinity. So the way we can take advantage of this is have x and y approach infinity and see what happens. So y approaches infinity when t approaches 4, because if I plug in t value very close to 4, I would get 1 over 0. That's approaching infinity, plus or minus. So then when t is 4, here I'm getting the infinite value. So if I plug that value of 4 into the equation for x, I get 3 over 4 minus 1. That's 1. And that's your x equals to 1 vertical asymptote over here. If on the other hand I inspect when does x approach infinity, that happens for t approaching 1. So now I take the value of 1, plug it into the equation for y. 1 over 1 minus 4 is negative 1/3. Negative 1/3, so that's my horizontal asymptote over here. So this graph you would get if you were to use Desmos to graph the parametric equation. The way you would do that is use this expression and that expression, just put both in parentheses with a comma in between them. All right, and now we are getting to some fun applications of parametric equations. Specifically, right now we will look into projectile motion. Before we do that, some reminders from physics that relate to speed or velocity, displacement or distance, and acceleration. So this equation is an equation that describes displacement for a motion that has constant acceleration. That constant acceleration is a. T is the time during which we monitored that motion. V is the velocity. V0 is the initial velocity at the beginning of the motion. And D sub 0 is the initial displacement, the height or horizontal distance at which we started. So, talking about projectile motion, the acceleration we will think about will simply be the acceleration due to gravity. And if we do that in feet per second squared, that's 32 feet per second squared, which means here your half of a will actually just be 16, or better, negative 16 if we consider up to be the positive direction of our motion. So the equations that we will be working with to describe projectile motion parametrically is your basic displacement is the rate or velocity, rate of the motion, multiplied by time. And we can represent that separately in the x and y direction. So in the x direction, the displacement, the horizontal displacement, is simply the velocity in the x direction multiplied by the time. The displacement in the y direction, or the height at time t, is simply the velocity in the y direction multiplied by time. So that's this part over here. Minus 16t squared is this term where we use the acceleration due to gravity downward in feet per second squared. And then we have the initial height over here, h0. And now I'm noticing how those Vx and Vy relate to the initial velocity itself. So I can represent that with a right angled triangle. This is the velocity vector, and then it has an x component and y component, where the x component is simply the velocity itself multiplied by cosine of the angle under which is the projectile released, and then in the y direction it's the velocity multiplied by sine. So then if I plug those in, I'm getting two equations for projectile motion that are parametric. In the x direction, I get the initial velocity multiplied by cosine of the angle under which the projectile is released from the horizontal direction multiplied by time. In the y direction, I get velocity multiplied by sine of that angle multiplied by time, minus 16t squared plus h0, which is the initial height. So what we are doing with this equation is at any point in time during the projectile motion, I can represent the position of the projectile using parametrically the xt, yt functions. So here is an example that involves a baseball player. So, baseball player throws a ball at an initial speed of 120 feet per second and at an angle of elevation from horizontal 18 degrees. He throws the ball from the initial height of 4 feet. So that's how high above the ground his hand is when he releases the ball. The questions are, where is the ball at 1.3 seconds? So horizontally and vertically, what's the location of that ball? What is the ball's maximum height? So the largest value of y we can achieve. And then, will the ball clear a wall that is 3 feet tall and 260 feet away? And those are the equations that we derived together for the projectile motion. Try the problem yourself first, then watch the solution. So, part A, where is the ball at 1.3 seconds? There I will simply plug in the time 1.3 into the equation for both the horizontal and vertical displacement. So, vertically, for y, I will have the term with the acceleration. So that's the minus 16 times time squared. Plus 120, this is the initial velocity, times sine of the angle, that's 18 degrees, multiplied by time again. And I will add the initial height, which is 4 feet. When I simplify that on a calculator, I will get 25.17 feet as the height of the ball after 1.3 seconds. The horizontal distance of the ball at 1.3 seconds is the simpler equation. It's the initial velocity multiplied by cosine of the angle times the time. So that's about 148.36 feet. In part B, we were asked to find the ball's maximum height. The way I'm going to do that is find the vertex of the parabola that represents the motion. So the vertex of any parabola in variable t can be found by looking at the coefficients of the quadratic equation a, b, and c and evaluating minus b over 2a. That's the x-coordinate of the vertex. So if I look at the quadratic equation, the coefficients are 120 sine 18 is my b, so I need to make that minus b. And my a is the negative 16 that I need to multiply by 2. So that tells me that the time at which the ball is going to reach its maximum height is about 1.16 seconds. The height itself that the question asked me to evaluate, then I can find by plugging the time into the equation of the parabola itself. So I will put 1.16 into this equation and get about 25.49 feet. And then finally, we were asked about the ball clearing or not clearing a wall that is 3 feet tall and is exactly 260 feet away. So the way I'm going to do that, let's look at a visual of it first. This is the trajectory of the ball. And then somewhere 260 feet away from the start of the motion horizontally, there is a wall that is 3 feet tall. So to evaluate whether the ball is going to clear that wall or whether the ball is not going to clear that wall, I'm going to find the time it took the ball to travel the horizontal distance of 260 feet. To do that, I'm going to use this equation, plug in 260 for x, and find the value of t. That is, using a calculator, about 2.278 seconds. And then to see whether the ball, after traveling for 2.278 seconds, if it cleared the wall that is 3 feet tall, I'm just going to find the height at which the ball is at that moment. That height I can find by plugging that time into the equation for y, which comes down to about 5.44 feet, which is more than 3. So the conclusion is yes, the ball will clear this wall. And here is the visual larger. So this is where the ball started at 4 feet of an initial height. Then after about 1.16 seconds, it reached the highest point, which has this horizontal and this vertical coordinate. Then at about 1.3 seconds, it decreased its height a little bit. And then here is the comparison with the wall. We evaluated that the height at the time when the ball traveled horizontally 260 feet was little over 5 feet. So that's more than the height of the wall, which is only 3 feet. So yes, it cleared the wall, and here is it shown visually. That's the entire presentation today. Thank you very much for working hard, and I'm going to see you for next lesson. Thank you all.